All right, well, without further ado, Connor is up to continue telling us about AVERT.
Yeah. Yeah, thanks, Terry, for the introduction really to the project. I've been the postdoc working on this for like last 3 years now, and it's been incredible. Working with AVO, working with Observatory, and more recently starting to work with Alaska-Aleutian, like getting to see all these like agencies and how they operate. It's been great. It's been also quite not pressing, but like seeing them and having their massive teams, and then trying to do all that at Lamont with a much smaller team. But it's eye-opening, and it really reveals like what the things need to be focused on. If you're trying to expand these sorts of things and share them with less well-funded agencies or smaller groups working in different parts of the world, like what aspects could be sort of centralized or like made better by collaborating widely as a community. I'm going to talk more about the system side and data, some of the things we learned. I would start by saying a lot of this stuff isn't necessarily new. Like AVO have been operating their logistics and their power systems and all these things like for many years before we came along. And that's one of the things we've also learned, is that using the knowledge that the agencies have built up over the last decades of working on these volcanoes is critical really for getting systems and networks in place that survive whatever conditions you're working in for more than a few months or half a year or a year, and really go on for years and years. So I think the vision I have here, this is perhaps a bit old and I should update it, but we have the sort of things that happen on the data and then the sort of field side of things, and then the like forward facing, how do we share those data with the broader community and make things open and real time and all those things. So really starting off, raw data that we collect is all made available directly through our webpage, just under this extension /archive. Any data products that we've been working on is made available under /products. We are actually recently hired a web developer who's going to be redeveloping a lot of our web tools and hopefully making those even better. But where possible, data go to existing repositories. So seismic data is all going to EarthScope. Magnetic field data, EarthScope can take that. EarthScope, actually, the FDSN network codes and FDSN codes for defining like mini-seed channels cover loads of things like temperature probes. You can put gas data, you can put pressure, lots of things. So taking advantage of things that already exist and already have all this infrastructure built around them, I think is really, really key. But that's not always true. In some places, you don't have existing repositories. An example is imagery. Essentially, every observatory has their own system for sharing their webcam data. Some of them make it available the last 10 years, but you have to go and just search through file system like lists. And some only have the last 24 hours. So aspects that we've been working on are how do we make those data streams available, and are there like protocols we can work on that then get sort of shared widely and people can help to develop as a community that will then sort of stabilize and make those sort of data available, so that say something happens, you want to look back at a previous eruption in 2004 and there was a webcam, you know how to get that data. And then there's a lot of tools about data sharing and visualization as well on the front end, but mostly it's been on the sort of field side. Okay. So really what I'm going to do some system development, infrastructure related things, and then sort of case-by-case data presentations of the different data streams we've been working on. This is what the inside of one of these Pelican cases that you may have seen. I think Max had some pictures inside the AVO huts. So the Pelican case has been modified, and in which most of the electronics are then mounted, acts as like a double wall to prevent any water ingression or anything damaging your electronics. And really, so yeah, we have our Centaur for seismic data. We have our GNSS receiver at sites that have a GNSS monument. We have a radio for telemetry, and then we have these little single board computers. And that's really, I think, where we differentiated ourselves from how things were already working here at AVO, by having one of these small, low power in the sense of computing power as well, computers that were on site that could do data archival, that could do some basic processing, and also do things like smart power control. So not always having all your things on when you don't need them to be on. And having something on site means that if your telemetry goes down, that's all running locally and you don't need to worry. And then when it comes back up, you have things that might do catch up on data. So rather than being too concerned that, okay, I've lost the last 2 months, but the instrument's now online, and you get not just your current real-time data, but you have some sort of catch-up protocol that like sends that interval so that you can actually complete your time series. And these have been great. They're a 2-3 watt consumption, so they do add a little bit to your sort of power load, but they can also be put to sleep if you're not using them. One of the aspects that we really want to explore a little more with these, and we think there's potential for, is edge computing. This means running processing like on site, so that rather than sending back all of your data that might be many megabytes, you can run the processing locally and then send back your like 10 kilobyte response, like result over telemetry, and it minimizes the strain you're putting on existing radio infrastructure or satellite infrastructure as well. And I have an example of where we've applied this in Costa Rica later on. And so this has really been like a try and do everything as well. So there's the hardware side, so trying to integrate different like electronic components, and then also the software programming to have it all running and locally. So this was one model, having a computer on every site. I think AVO in the last couple of years have also adopted a similar model where they have a single board computer at one of their hub sites that acts as like a buffer, so that if the telemetry is down, then they still have something on island that is collecting and archiving data slightly closer to their home servers. Okay. So you've seen these pictures before. This is what it looks like in Alaska. And you can see you've got 270 watts of solar panels. This site has a wind turbine, 50 watts. Inside there's 24 100 ampere hour lead acid batteries that weigh 70 pounds each. And there are 2 of those on one side. In Costa Rica, it looks very different. And this is like we're saying, when you kind of want to work like with the conditions that you're deploying your networks in. So in Costa Rica, we can get away with, because it's basically equatorial, a small box with 2 100 ampere hour batteries and 2 like a 200 watt solar panel. And that's great. That basically keeps everything alive, no problem. So really adapting, but inside these Pelican cases are essentially exactly the same systems. So it's just changing the power infrastructure to best suit the deployment that you're working on at the time. So we also log the data that's being output by the solar controllers in these power systems, just to get a sense of, okay, how are they performing through the year? You can see the dark months when you basically get no battery charging. This is CLNE, so it is these pair of sites. The one on the right-hand side is the lower one with the wind turbine, and the one on the left-hand side is the upper one with no wind turbine. And I can see a little bit of what I'm saying about these duty cycling modes where you turn things off when you don't need them. If we left everything on, this system would consume 13 watts average. But by having it on duty cycling, in this case, we were turning off the radios, we were turning off the single board computers in between catches. We were doing everything we could to minimize the power. And that obviously introduces latency in your like data telemetry. But you're able to reduce that to 2 watt average power consumption, which is much more manageable through the long dark rainfall winters. And you can see that this is the low voltage disconnect level. If you fall below that, everything turns off, and we never got close. So really encouraging. Lessons from this as well is, how much does a 50 watt wind turbine contribute? You'd think the Aleutians, super windy, be great in dark months. I think I identified for this period here, you can see low solar panel voltage. It's probably dark, maybe covered with snow or something. And you can see this little bump here. And you don't see a little bump, the corresponding one on the site that doesn't have. These are basically co-located. So that's the contribution that wind turbine is making. So maybe it's not great, but it's not negligible, right? So having that means that might keep it on for a few extra days. So it could be worthwhile. But they do also have a tendency to explode. They don't, like, as soon as they get a little bit of a like grit or something in them, the bearings go and they just shake themselves apart. Okay, data telemetry. I think we've seen a little bit about the VSAT, and Terry mentioned BGAN. BGAN was great. It was a bit expensive, and the satellite itself did break during the deployment. So we were exploring other options, and Starlink was really starting to sort of take off in terms of coverage. The costs were coming down. It's pretty cheap as things go. And then again, thinking about like the mindset of we don't necessarily have the budget to make a big VSAT installation. Can we still do these things where we have satellite telemetry in real time? And Starlink allows you to do that. It's somewhere between $60 and $150 a month, depending on where you are in the world. So much, much cheaper than alternatives. And yeah, in Costa Rica, again, power is not much of an issue there because of the equatorial location, but we're able to run this whole thing on a DC power system and have no outages after a few hiccups in the first couple of months where we added a bit more storage. And again, you can operate these things in duty cycling. I was doing some testing. You can turn a Starlink off and turn it back on, and you have internet in between 30 seconds and a minute. So if you really didn't mind too much about having a bit of latency on your data, you could have one of these that turns on once an hour, and you still get all of your data. So you're not maybe getting real time, but you're still not having to make a site visit, or you're still getting data maybe up to an hour before whatever destroys your site, perhaps. Starlink Mini is an alternative. This is the Starlink Classic. It's about 30 watts. And the Starlink Mini, if you're again only having to send a little bit of data, the bandwidth is lower because it's a smaller satellite receiver. Does consume about 13 watts, 13 to 15 watts from my extent. Okay, data streams. Geodetic data. Terry did a great job introducing this, saying we've doubled the number of GNSS monuments we have on Okmok. Critically, OKCF and OKBR were added, and that allowed the center of inflation is somewhere in the middle of the caldera. So it added that constraint on the east and the southern sides of the center of inflation. And this is data taken from the AVO processing webpage, just showing since July 2024. I think in about October or so, there was an acceleration in inflation. And you can see this is vertical, north-south, and east-west. They all kind of go up about the same amount. The ones that are north and south of the inflation go the right directions, which is nice. And the same with the east and west ones. That was a nice thing to have. Seismic data. Yeah, as Terry said as well, we've gone from 2 permanent continuous seismometers on the islands of 4 mountains to 5 plus 6 campaign stations for the 2022 to 2024 period. And this is the data availability. You know, the campaign sites you were visited, so you get essentially continuous data. And these are telemetry gaps that, you know, occur when there are small outages in the telemetry. And these are the CLNE and CLSF, the 2 sites that we're looking at. And I'll talk more about this tomorrow, but a bit of a spoiler. There's some really interesting swarms of earthquakes in Cleveland in July 2023. This is 8 days and 8,000 earthquakes in those 8 days. And the y-axis is inter-event time. So just looking at how the swarm evolves through time and how closely spaced those earthquakes were. Magnetic data. There are lots of places that we've put these magnetometers, and so far haven't yet had much opportunity to really explore the signals that we might see. I think, yeah, Joe Biasi, Wyoming at the back to the right, has done some modeling of various past intrusions and eruptions to look at what you might see if you had stations, and found that, you know, in certain locations, if you can get close enough, you ought to be able to see the magnetic field change. So we have 2 on Cleveland near this, 2 in Okmok, 1 outside and 1 inside, 3 at Poas, 1 on the flank, 2 right in the crater. And then this isn't AVERT funded, but it's an SF project that Joe and I have together. And we've installed a large network of 6 plus a number of low-cost magnetometers that Joe's been developing at Askia volcano, which is very, very similar. I think I haven't done my 2 maps 1 scale trip here, but they're basically the same. They're about 10 kilometers across in both cases. So very similar types of systems. And you can do various things with that. So this is the XYZ component of the magnetic field. Fluxgate magnetometers that we're using are temperature sensitive. You can see this is temperature through time. You can see a corresponding slope here, but you can correct that quite nicely. Sorry, this is absolutely the temperature is this one. Corresponding slope, but you can do some corrections, and then we are going to explore this a little more. But the really interesting thing at Askia is that the magnetic anomaly inside the caldera is like 20,000 nanotesla. The field here in Iceland is about 50,000 nanotesla. So there's a huge drop in absolute magnetic field for our sites that are inside the caldera and just a few kilometers away that are, about what we would expect them to be. So there's more to come. Explore with that. Soil probes, CO2 soil probes. This actually, I think, was Paso Girona, who's at UAF, who started this at Okmok. He installed 2 CO2 soil probes and 2 temperature soil probes at different depths at 2 of the sites inside the caldera. One of those CO2 probes didn't work, so that was returned and replaced, and we had it sitting around, so we said, why don't we put it at POAS? And we just chose a site and we put it at POAS. This is what it looks like. They're about this big. They're super easy to install. They're very low power, fairly low cost. I think $2,000 to $3,000 or so. And yet, through time, this is the CO2 we're measuring. This is February this year. And this is the seismic amplitude measured at a nearby seismometer. And you can see these periods in yellow are when we have infrasound pulses. These are explosive events, those phreatic eruptions that you see in those flips at POAS. Okay. And the corresponding increase in concentration at the same time as you have this increase in seismic amplitude, it kind of stays high during this period, drops when those phreatic eruptions, explosions stop, and then goes back up when they start up again. I don't think we have any idea exactly the mechanism behind this. And we actually had one of the teams that visited for the workshop in March. Actually, a few teams were making a sort of walking survey of that area with accumulation chambers to try and get a sense of like whether we'd found some sort of hotspot or what was going on. So there's more work to be done, I think, trying to understand these, but they're promising in that, one of these sites is maybe $15,000 to $20,000. And this could be done for a fraction, like 20% of that. Or you can just add them to any site that you already have. Why not? Okay, imagery. Again, this is POAS because, again, this example is where we've been applying this, although we've been doing something similar we have done something similar at Cleveland, looking at characterizing and classifying the images that we're collecting. So this is the infrared camera that we've been using. It's installed inside a pelican case with a germanium window. This is what it's looking at, POAS Crater Lake, with different vents, and these fumarole banks that's in that vent where they made those noble gas measurements with the portable mass spectrometer. This is where that camera is. This is the field of view that it has. Terry already had this in hers, but this is the sort of images and things that it captures. And this is what we want to see. We want to see these explosions in as much detail as possible. What we don't want to see is clouds. And for example, in the Aleutians, half the time your webcams are just gray images of nothing that are quite large in terms of data, raindrops, snow, all these things covering your lenses. And what would be really nice is on site having a computer that is running some analysis code that characterizes, okay, is it clear? Is it not clear? And changing the rate of capture and changing whether or not you're even sending those images back to your server. So an undergraduate student at Columbia, Kazuya Shikin, I've been working with the last year or so, has been working on this, and he has developed something that uses some of the features that we can see in the field of view of the camera. These fumaroles light up really nicely. The lake as well, of course, when it's full of water, is that temperature of the water is elevated above the background, so it shows up really nicely as well. And actually, you might think this would be a bit frustrating, having part of your image just being a fence kind of close to the camera, but it's really useful for saying, this is clear, but then I can't see anything here. So it's like probably completely clouded out, just conditions. And this can run on those single board computers that we have in about a second and a half. So really quick to do, and then you can vary your capture rate. You can do whatever you want with those results. So that's something that I think was really cool aspect that we can continue to explore. He took the results of that, of those characterizations, and took all the good images and looked at how you can perhaps track the lake extent at POAS. POAS, the crater lake, goes up and down depending on volcanic activity. And you can see in 2023 it started, 2024, the lake decreases, stays low, rainy season, it increases, and then activity starts again and it rapidly decreases again. So a really cool application, but you really want to find all the good images and you need to be able to characterize, classify images using that. A couple more things, I will keep going. Microgravity, one of the teams that joined us for the workshop deployed this MEMS-based gravimeter. These are low cost in the fact that they maybe cost $10,000 to $15,000 rather than $100,000 to $150,000 and can be installed in the field. They're fairly low power and they've made the first measurement. This is preliminary data, not to be shared, blah, 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 of tracking earth tides. This is the first time this has been done with this type of gravimeter on an active volcano. And these spikes all correspond with the largest eruptions at POAS in this period. Signal to be explored still. It's very preliminary. And then I think really Eureka stuff we've talked about enough. This is the 2 maps, 1 scale, showing the similarity between Cleveland and Eureka at the summit, except this is a lava lake and this is a dome forming event. And our objectives are to install sites, as Terry said, here or perhaps here, and explore ways that we can make a mini network perhaps. So that's it. These are some future developments, but I will just leave it at that.
Thanks, Connor. Does anyone have any questions for Connor while we switch talks?
The idea of using a computer program to kind of quantify visibility is very interesting. How do you think they would be able to make it differentiate between we can't see these features because it's cloudy or foggy, or we can't see these features because there's an eruption going on?
Yeah, great question. Something that he has tried to do is look at whether you can say, okay, it's clear, but there's a plume blocking one of those features, because that's very common at POAS. And so that's why it's useful to have a number of like features within your image that can be used to get a sense of, okay, this aspect is clear, but I can't see the lake feature. So perhaps it's still useful or interesting, so we'll keep it. And then someone can actually visually analyze it to see, okay, was it an eruption? Also looking at trying to bring in the infrasound, trying to bring in the seismic data, other data streams to help you. Again, with a single board computer locally, you've got the possibility of collecting your infrasound data and incorporating it into your analysis in situ before you make any decisions.
And nothing's actually thrown away.
It could all be recorded locally as well. So if you really wanted to go and collect it all.
All right, well,